there's some important features of the Friedel-Crafts alkylation that we want to be aware of. So this reaction is a bit more specific or a bit more finicky than the other electrophilic aromatic substitution reactions that we've talked about. So there's some additional things here that you need to be aware of. The first thing has to do with the alkyl chloride that you use. Methyl primary, secondary, and tertiary chlorides all work well. So you have a pretty good arrangement of substrates that you can use here. So things like, here's a methyl chloride, here's a secondary chloride, and here's a tertiary chloride. All of these would work in the Friedel-Crafts alkylation. The second thing to note, which is really important, is that the carbon bonded to the chlorine in the alkyl chloride must be sp3 hybridized. So what that means, just to show you an example, here's a primary chloride. We want to specifically look at the carbon bonded to the chlorine. That must be sp3. Because it's sp3, this reaction, or this organochloride, would be expected to work in the Friedel-Crafts alkylation. But if you were to change that to a vinyl chloride, or have an alkyne here, where now what we have is an sp2 and sp hybridization, these will not work in the Friedel-Crafts alkylation. And if you think back to the mechanism, the reason behind this is the fact that if you were to form a carbocation, think about the carbocation you would form with the sp2 carbon. That would be a vinyl cation, which is very unstable. And likewise, having a cation on the end of a triple bond is very unstable. So that's why we need the sp3 hybridized carbon. The third thing can be a good thing or a bad thing depending on what you want, but if you leave this reaction to react, polyalkylation can occur. Now we have ways to monitor reactions, but if you were to take benzene and react this with methyl chloride and AlCl3, we're going to do the Friedel-Crafts alkylation and put the methyl group on the ring. And if you monitor the reaction closely, you could stop and isolate this product. But if you allow the reaction to keep going, so over time, you're going to end up getting additional products. So we can end up putting a second methyl group right here. Or if you continued to let this react, you could eventually get several methyl groups on the ring. So if you want multiple groups on the ring, then you can just let the reaction go for an extended period of time. But if you want to stop it with just one, that is possible. The next thing is something that I talked a little bit about earlier, is that carbocation rearrangement can occur. And it all depends on the organochloride substrate that you start with. So let's look at an example reaction. I'm going to start with benzene. And for my organochloride this time, I'm going to use isobutyl chloride. And we'll react this with our Lewis acid, AlCl3. And what you would probably expect here is for this carbon, where the chlorine is at, to be bonded to the ring. So the expected product would be this. But if you do this reaction, the actual product is going to be tert-butylbenzene. So why is that? What you want to do is always look at your Lewis acid base adduct and the carbocation that forms. So anytime you go to do this reaction, draw your Lewis acid base product. From there, go ahead and lose the chlorine and draw the carbocation that forms. What do we have here? We have a primary cation. Thinking back to organic 1, remember that carbocations will rearrange to become more stable. So what can this do? This can undergo a hydride shift, and it will happen with this hydrogen on the tertiary carbon, and that can shift to the carbon where the carbocation is at. So the hydrogen, I'm not going to draw it in, but it'll go up here, and we end up with a carbocation on the tertiary carbon, and that's more stable. So then it's this tertiary carbocation that leads to the actual product that's formed. The final feature to be aware of has to do with the benzene that you start with. So if you just start with benzene and do a Friedel-Crafts, it should work. But if you were to start with a substituted benzene, meaning you have some group on the ring, and you try to do a Friedel-Crafts reaction, depending on what this group is, the reaction may or may not work. And there's a couple of important groups to be aware of. The first are amino groups. And this could include an NH2 or carbon substituted amino groups. So you could have NH2, NHR, or NR2. If you have an NH group on the ring, you're not going to get any reaction. Why is that? The problem is that the nitrogen lone pair is especially Lewis basic. And what that will do is it will react with the catalyst preferentially over the lone pair on the chlorine. So this lone pair ends up reacting with the aluminum trichloride, and we end up getting this Lewis acid base adduct, and the reaction gets shut down. So I'll just say the catalyst gets tied up and no EAS reaction occurs. The other problematic groups are strong electron withdrawing groups. Now this is something we're going to talk about in a lot more detail, how to identify strong electron withdrawing groups. But these are things like a nitro group, a CN group, SO3H, things like that. These strong electron withdrawing groups, if you have one of those on the ring, what we're going to learn later on is that these groups deactivate the ring, meaning it makes them less reactive. So I'll just put this, the electron withdrawing group deactivates the ring and makes it unreactive in the Friedel-Crafts reaction. One important feature to distinguish here is this is just the case for Friedel-Crafts reactions. If you do halogenation or nitration or something like that, these electron withdrawing groups aren't nearly as problematic. So this is specific to Friedel-Crafts reactions.